Welcome, Chem 30, week 10. What this means is you have one more week, as in week 11, after this one, of new material for Chemistry 30. And then in our 12th week, we're going to have a whole course assignment. So obviously there's not a final exam, there's not a diploma exam, but we will still do an assignment that encompasses everything that you've done this year. And there won't be any new material that week. There won't be any podcasts or anything that week. Simply a matter of you going back through things, making sure that you stayed accountable at this. I'll open up more help opportunities in case you've got questions through the week. And then, Chem 30 accomplished, which is fantastic. Now, what we're going to continue on is kind of a little bit of a change of pace from Le Chatelet's, to say the least, but it will continue on with equilibrium, of course, and with equilibrium constants. Now, specifically, though, we're going to look at equilibrium as it relates to water, which I know sounds odd, but bear with me. And then we'll look at equilibrium as it relates to acids and as it relates to bases. And that'll take us right through to the end of the week. Now, first things first, a lot of this starting podcast is going to be a huge amount of review from Chemistry 20. And if you think way back to Chem 20, when you were learning about strong acids and strong bases and weak acids and weak bases and how to calculate pH and hydronium concentration, etc., that's the review stuff that we're getting into. Now, first, a couple reminders for you. Starting off, if you take pure water and you have sensitive enough ability to do this, you will actually see that it conducts electricity, which is kind of weird. The conductivity testers that we have at HTA, they can't actually measure this, right? They're just not sensitive enough. But if you get one that is good enough, absolutely, there's a slight amount of conductivity. Now, the only way that anything conducts is if ions are present. So that means that in some way, shape, or form, water must have ions. And I'm not talking about impurified water. I'm talking about pure as it can be, the pure substance, water liquid, H2O. Now, here's the deal. Ultimately, a small amount, and you haven't seen this in a while, H3O plus stands for hydronium, just in case you need the reminder, right? Hydronium, there we go. And hydroxide, that one's familiar, of course, are present because of what we call the auto-ionization of water. Now, the word auto means it happens without making it happen. It's automatic. And the word ionization literally means where ions form where they were not before. So if we take water and let it really just be, we end up with an equilibrium where a very small portion ionizes to hydronium and a very small portion ionizes to hydroxide. Now, seriously small. Let's think about what this number is. 0.12345 there's to the 7th spot moles per liter. That's what that means, right? That is your concentration of hydronium, and that is your identical concentration then of hydroxide. This is teeny tiny, guys. We're talking about a fairly small concentration. However, it happens, absolutely. Notice as well that they are proportional to each other. From a mole ratio perspective, the moles of hydronium in pure water are identical to the moles of hydroxide. In other words, the concentration of hydronium is identical to the concentration of hydroxide in pure water. Now, ultimately, what this relates to then, of course, is an equilibrium. Now, why? Because of this, guys. If there is an equilibrium system between water and its ionization to hydronium and hydroxide, an equilibrium system exists. And we're really specific in this one. We don't call it simply Kc. Instead, we call it Kw because it is specific to water. Now, when this is worked out, ultimately what it comes down to is think about what would be the equilibrium law for this equilibrium system. Water would be left out because it's a pure liquid. So we would simply have the concentrations of the products over the concentration of reactant not included over 1. And that's what you see right here. This is the equilibrium law for the autoionization of water. And if you plug in the values that we got from the previous page, the molarity of the hydronium to the molarity of the hydroxide, multiply those two things together, dun, 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 we have the water autoionization constant. And this thing is in your data booklets. It's not something that you have to memorize, but it's one that certainly comes in handy. So if you go in your data booklets to the 3rd page, back and back and back, this is where you'll find it. So take note of that. Be aware that it's there. It's not something that would have ever had to have been memorized. It's just something you need to be aware that it exists and that it relates specifically to the equilibrium of water when it ionizes. Okay, let's keep going here. Just a side note and something to remember that should hopefully kind of tweak your memory from last year. Any solution of pure water has a pH of 7. And in terms of the logic of this, well, pH, of course, relates to the logarithmic scale, taking the logs of the concentrations. And it means if you've got 7, that the hydronium and the hydroxide concentrations are perfectly identical. They're the same. In other words, they cancel each other out, and we have a neutral substance. Whew! Hey, lots to take in. A little bit more here. This is more review. Acids are able to ionize to produce hydronium, right? I already mentioned that, but I'll say that word again so you don't forget it. Hydronium. Not new this year, new last year in Chem 20. And the next thing too, and these are familiar from last year, but you may have forgotten them. If you've got an acidic solution, guarantee that the concentration of that hydronium is going to be greater than the typical neutral, right? Greater than the 1.0 times 10 to the negative 7 mole per liter. Vice versa then, if hydronium concentration is higher, then of course hydroxide concentration is going to be lower, right? Because the hydronium concentration is more, it is an acidic solution. It counteracts and overcomes the hydroxide concentration. The opposite, of course, is going to be true when it comes to a base. A base will ionize in water, definitely if you have something like an anion or an NH3, for example. There's also a dissociation that comes into play here too when you're dealing with a metal hydroxide, right? Something that has metal and has hydroxide in it. But ultimately, if you have a basic solution, now we're going to do the opposite, where the hydroxide is greater than 1.0 times 10 to the negative 7 molarity, whereas the hydronium is less than that. So in this circumstance, we have hydroxide concentration being greater than that of hydronium, hence the basic characteristics take precedence. Alrighty, now from the equilibrium law for water autoionization, the one, in other words, that I highlighted in red right here. Here, I'll highlight it in green. There's that equilibrium law, right? We can take that and utilize it because we know Kw, right? 1.0 times 10 to the negative 14. So here's 2 manipulations of that law that come in super, super handy. In other words, we always have Kw. That's a done deal. And as long as we have hydroxide concentration, we can get hydronium. And vice versa, as long as I have hydronium concentration, then I can get hydroxide. That's super useful. Just by knowing Kw, there's a massive wealth of information for any equilibrium system. Okay, for example, let's say that we're trying to calculate the hydronium and the hydroxide concentrations of a 2.5 times 10 to the negative 3 mole per liter, or molarity, hydrochloric acid solution. Now here's the deal with HCl. You may or may not have remembered this from last year, but HCl is a strong acid. And whenever you have strong acids, guys, we'll talk more about this in a future podcast, you have what's called 100% ionization, which means that every last bit of that HCl ionizes. And in terms of an equation, this is a review from Chem 20 again, but I want to see this when you're going through questions. You're going to take your HCl, and the ionization means that it reacts with water. Bringing you way back to Chem 20 now, okay? When it reacts with the water, we have what's called a proton transfer. So the hydrogen on the HCl transfers to the water. So I'm going to show that transferring going by. Because this thing is quantitative, it's 100%, it's a strong acid, it's a one-way arrow, okay? So from that one-way arrow then, I can look at this and be like, okay, what's going to happen? Well, it transferred. So we're left then with Cl negative aqueous and hydronium, no longer water, but this is why it's characteristically acidic, right? Now here's where things get kind of interesting. This is a circumstance that because this is 100% ionization, that means that the concentration of that strong acid, this HCl, is going to be identical, and it's 1-to-1 to the hydronium concentration. So yes, we're told concentration of the HCl is 2.5 times 10 to the negative 3 molarity, but then I can take that, knowing it's a quantitative strong acid that 100% ionizes, and I could say the concentration of hydronium is 2.5 times 10 to the negative 3 moles per liter as well, right? Why? Again, because it is a strong acid. And I mean, this is stoichiometric. Ultimately, you're taking this, dividing by the 1 mole of HCl, multiplying by the 1 mole of hydronium. There we go, 1-to-1 ratio. In terms of the math of this now, we have the hydronium concentration. And if I have that, I have everything I need with the autoionization constant to get the concentration of hydroxide. So we're good to go. So consider, at this point, this part of the question is already done. I just figured that out because it's a strong acid. This part of the question can be figured out with our new formula. Here we go. Kw, again, if you forget it, it's in your data booklet, 1.0 times 10 to the negative 14. Just like any equilibrium constant, it doesn't have units. Divided by the concentration of the hydronium, 2.5 times 10 to the negative 3 moles per liter. Number crunch in your calculator. Be careful, guys. I usually, when I do these, I'll put brackets around these just to make sure my calculator is not trying to mess up how your numbers go. Okay, be smart about it. In the end, we get, and we need to keep our 2 sig digs, hydroxide concentration is equal to 4.0 times 10 to the negative 12 moles per liter. And there you have it. Done and done. We've just utilized the autoionization constant for water. Okay, give you another example where you got to do a little bit more work to get the concentration before you can utilize it. So what about this one? Exact same goal of the question. Calculate the hydronium concentration, calculate the hydroxide concentration, but this time I'm giving you a mass of something. Now, a mass of what? Well, look what we have here. It's got hydroxide in it. Think back to Chem 20 again. This is a metal hydroxide. Sodium the metal, hydroxide the OH. That means automatically we are dealing with a strong base. And characteristic-wise, if you have a strong base, then you're dealing with a circumstance that this thing put in water, aqueous, 100% dissociates into its individual ions. That's what dissociation is. This is not a chemical reaction. This is simply a process of dissolving. Listen to the beginning of the words. Dissolve, dissociate, right? Okay. Now, here's the mass of sodium hydroxide going in. Here's the volume of water it's put into. Regardless, it's a 1-to-1 ratio between the sodium hydroxide and the hydroxide. So that gives us something that we can play around with here. Okay, let's get to it. Mass of sodium hydroxide, 1.6 grams. Molar mass, I'll figure out now, 40.00 grams per mole. And the volume was given us to the question, 5.0 liters. So let's figure out what N is, because we got everything we need to do that. N is equal to mass over molar mass, plug in your values, and don't round anything yet, guys, right? Take the time. We've got 0.04 moles. Now, remember what I said. We're dealing with that 1-to-1 ratio. So we're going to divide by the 1 mole of sodium hydroxide times by the 1 mole of hydroxide. And sure enough, then we know that they're going to be identical. Now, whether you calculate concentration now or calculate it after, it's going to be the same either way. So I'm going to do it over here. I've got room. C equals N over V equals 0.04 moles divided by our 5.0 liters. And we're going to get a total of 0.0080 moles per liter. Therefore, one of our questions has just been answered. The concentration of hydroxide is equal to 0.0080 molarity. There we go. Now, same. How do you get hydronium concentration now? Well, the handy dandy recognized equilibrium law for the autoionization of water. H3O plus equals Kw over hydroxide concentration, which we just got, 1.0 times 10 to the negative 14 divided by 0.0080 molarity. And our hydronium concentration is going to be equal to 1.3 times 10 to the negative 12 moles per liter. And there we go. Both things have been figured out, guys. Now, technically, that's a new formula. It's a pretty simplistic one, to be honest with you, but it is one that you wouldn't have been introduced to in Chem 20, even though the concept of water having these ions in it would have come up. Okay, let's get into the straight review now with pH and POH. POH in particular was a new concept for a high majority of you for Chem 20. Now, ultimately, the whole goal of a pH scale and vice versa, POH, is to figure out how acidic or basic something is. So going way back in your memories, usually this goes from 0 to 14. Ultimately, numbers below 0 exist that are highly, highly acidic. And numbers above 14 exist that are highly, highly basic. But ultimately, 0 is our neutrality, right? So, or it's not 0, 7 is our neutrality. So when you have a pH of 7 or vice versa, a POH of 7, we're dealing with neutral. Now, here's those formulas. If you were taking a diploma this year, you'd have to have all of this memorized. Lucky you. Hopefully you guys are still making formula lists or something that you are able to easily keep track of these. If not, something worth doing this week as you're approaching that final assignment, getting all your formulas together on one sheet so that you're better able to organize your brain when you're doing the assignment. Anywho, this is, like I said, straight review. So when you're trying to calculate pH, as long as you have the hydronium concentration, you're good to go. Logs should be more familiar to you this year than last year because you would have covered them from a math perspective. Now, into hydronium. Hydronium concentration can be found by essentially doing the inverse of the log, right? Which again, wouldn't have made much sense in Chem 20, but should make more sense now. To do this, we take 10 to the negative exponent of the pH. Super important, guys, that you are not forgetting these negatives. People don't, it'll mess up your answers. It's the negative log and it is the negative pH. Another huge reminder to you is this. This is big and I will be looking very carefully on your assignments that you are following this. The number of decimal places, so that means after the decimal, okay, of the pH value is what is actually considered to be significant. Now, I'll give you an example. If I have a pH of 6.82, what that means is this only has 2 significant digits. The 6 is simply about place value. The 8 and the 2 are significant, okay? So, give you another scenario. What if I told you I have a hydronium concentration of 1.34 moles per liter? That would relate then to a pH of where you put a digit here, and then you would have to have 1, 2, 3 digits after to match the 3 numbers in the concentration. We'll put this into practice. Let's try a couple here. So moving on. Like I said, straight review, guys. You've done all of this in Chem 20. Calculate the pH when you've been given a hydronium concentration of 2.7 times 10 to the negative 5 moles per liter. I want to still see formulas, please. For these ones, this is not a unit analysis situation. You need to show the formula that you're doing, okay? pH equals the negative log of the hydronium concentration. There's that formula. Now plug in what you know. Yes, you should plug it in with units. This is not new. So 2.7 times 10 to the negative 5 moles per liter. You can use it as capital M molarity if you want. That's fine. We're going to end up with a long number, 4.56863 ... Now here's where those sig digs come in. This concentration has two significant digits. So my pH also needs to have two sig digs. The 4 is not significant. After the decimal place is, this is 4.57. Done and done. There's our correct pH. Hopefully you see that and your brain goes, oh yeah, I kind of remember this from Chem 20. That's sort of coming back to me. Once you get used to them, in all honesty, these pH calculations, they get pretty easy, right? Like in the scheme of mathematical equations, these aren't so bad, okay? All right, let's do this one. What if we do the opposite? And I say, okay, what is the hydronium concentration if I give you the pH of 10.33? So now we have to utilize the other equation that I just reviewed with you. Hydronium concentration is going to be equal to 10 to the exponent of, don't forget the negative, pH. And in this case, that means 10 to the negative 10.33. Do your number crunching. We get 4.67735 ... times 10 to the negative 11 moles per liter. Now think back. This has two significant digits. Only the numbers to the right of the decimal place are significant. So hydronium concentration, therefore, is equal to 4.7 moles per liter. And there are indeed my two sig digs. Notice something else here, guys. Concentration, of course, has units. You can either use molarity or you can do moles per liter. They mean the same thing. pH, on the other hand, is in this question, is unitless, and that's nothing new. Same. Now, as we move into pOH, the exact same rules apply. pOH has no units, and the rules for significant figures with pOH are identical to that for pH. And these formulas, honestly, are super logical too. They're the exact same as pH, except we are using pOH in replacement and hydroxide in replacement of hydronium. Okay? Otherwise, same. Still pay attention to those negatives, please. Makes a huge difference in your answers. One more formula, total review from Chem 20. The pH and the pOH, this is a hugely useful formula, by the way. It's a nice time saver. They will always add up to exactly 14, right? This is a done deal and very, very useful when it comes to questions where you're asked to find pH and pOH and hydronium concentrations and hydroxide concentrations, which, no surprise, you are going to have to do. Okay. Little reminder for you when it comes to the pH scale in terms of how these work. The lower the pH and the higher the pOH, the more acidic a substance is, right? These are inverse of each other. They're opposite. Vice versa, the higher the pH and the lower the pOH, the more basic a substance is, right? These work in opposites of each other. Okay, let's try another question where we incorporate those new formulas. Check out this one. This one asks you to find not just a pH and not just pOH, but both. And all that you've been given is hydronium. Well, hydronium is super useful when it comes to pH, but is not directly related to pOH. So keep that in the back of your mind. We need to do something to get to hydroxide concentrations. There is more than one way to do this question, guys, right? A multitude of different methods. Here's the one I'm going to start with. I'm going to be like, okay, I've got hydronium, so I'm going to figure out hydroxide concentration by using the water autoionization constant. Kw over hydronium concentration equals 1.0 times 10 to the negative 14 divided by 2.7 times 10 to the negative 3 moles per liter. Number crunch away. Do not round this value. This is something that's really important as you go through these questions. Do not round until the end, right? Otherwise, you're going to end up with less accuracy than you would. So keep that long number on your calculator, utilize it, and don't round until we're totally finished. Okay. At this point, we've actually done nothing the question has asked. We don't have pH or POH, but having that hydroxide concentration can certainly be used, because now what I could do is go, all right, I know that POH is equal to the negative log of the hydroxide concentration, and I just figured that out. So negative log, take the unrounded value, 3.7037 ... times 10 to the negative 12 moles per liter, and I end up with a wonderful POH. Now be careful here, 2 sig digs, so my answer has to have 2 sig digs, which means 2 digits after the decimal, 11.43. There's one of the things we've been asked to find. Now here you've got options. Potentially what we could do at this point is we have pH. And maybe we would have done this first, right? Negative log, it's not like this has to be done in a certain order, of the hydronium concentration equals negative log, I'm going right back to the question now, 2.7 times 10 to the negative 3 moles per liter. pH is going to be 2.57. Awesome. Okay, we just did the question, got the answer. Like I said, more than one way to do these. There really is. So you got to find out what's comfortable for you. I'll give you an example. What if I started with this, with finding the pH? I could have done that. I had the concentration of hydronium. And then what if after I got the pH, I decided to use this formula instead? And I went, I know that POH is going to be equal to 14.00 minus the pH. That's just that rearrangement of pH plus POH equals 14, right? I just found the pH. 14.00 minus 2.57. I would have used the unrounded value, right? And we get the wonderful world of a POH equal to 11.43. Oh, look! Same as this over here. So more than one way to go through these, guys. As long as you are showing process, showing work, and getting to a correct end answer, I'm happy. Okay, like I said, review. Lots of stuff from Chem 20. I want you to practice this before we get into the new stuff, please, because you have to feel really, really confident into it for the remainder of our concepts for this week. And in all honesty, it's really important for our concepts going into next week as well. So do number 1, 2, 3, and 4 from your weekly assignment 10, and I will talk to you shortly in podcast number 2.